Welcome again to antenna as a component. In this video, we'll learn how to plot a radiation pattern of an antenna. So the purpose is to draw an antenna radiation pattern. So we follow actually specific steps to do so. Starting from the given, we will be given either the radiation density, intensity, or the electric field, for example. And the first step is to normalize this one, just find its maximum and normalize. Then the second step will be to determine the position of the nulls, and in order to calculate what's called beamwidth between nulls. Then if it was there, we also calculate the side lobes, and finally we calculate what's called half power angles in order to calculate half power beamwidth. So I think the best for this kind of explanation is to have an example. So the example is telling that draw the radiation pattern of a short dipole. This is the first type of antenna normally which you will face in an antenna course. And in two principal planes, phi is equal to 90 and theta is equal to 90. And what is these two planes? Actually, if you plot x, y, z, we know that if theta is the angle with z, right? So theta is like this. Phi is the angle with x. And in this case, if phi is equal to 90 and theta is variable, this means you are in this plane, right? XZ plane. So phi is equal to 90 means this is YZ plane. And the other one is theta is equal to 90. Theta is equal to 90. Theta is equal to 0 when z is equal to 0. And if you move with z, you will land at the end when it is 90 like this. You will land in the xy plane. So theta is equal to 90 means xy plane. So what is the first step? As I have said in the previous slide, you just need to make normalization. So this is our power density. You need to find the maximum. Sine maximum is just 1. Then the maximum will be the magnitude of the sine here, so which is this one. Then we divide by 50. We will reach the power density equal to sine, of course, normalized sine square theta. Then we will go to the principal planes which we are asked to plot in. We'll start with phi equal to 90 degree because this is actually the one which have more effort. And once we put phi equal to 90, nothing will change actually because it is only dependent on theta. Now we find the maximum location, and we know that maximum is equal to 1 because this is already normalized. Then we will equate the power density normalized to 1. Then we will get sine square theta is equal to 1. Then we just make the root in the two sides. Once we make the root, then we get sine theta is equal to plus or minus 1. If we make sine minus 1 of the two sides, sine minus 1, inverse sine, then we will get that theta is equal either to pi over 2 or minus pi over 2. So we have two maxima actually. So if we plot this plane, we said that this will be the YZ plane. Where is theta? Theta is the angle with Z. And where is its maximum? When it is equal to 90 degree. So maximum actually will lie on the y-axis. This one and this minus 1. Then we will go to calculate the nulls here. So what is the null? Null means the power radiated is equal to 0 at this specific point, or the power density is equal to 0. So simply here what we have done, we got the normalized power and equate it to 0. and then just follow similar step, take the root and make sine minus 1. Then when we take sine minus 1 of sine theta equal to 0, we'll get that theta is either equal to 0 degree or theta is equal to pi. And this means that in the z-axis, because theta is equal to 0 in this direction and this direction, so in z-axis we have nulls. This one theta is equal to 0 and this one theta is equal to pi. Then of course one important parameter here which we can calculate, beamwidth between nulls. Just to make subtraction of these two, pi minus 0, we got pi, which is actually 180 degrees. Last step is to find the angles of half power, and this simply again is just equating the bar density to half, because this is still normalized, because maximum over 2 and maximum is 1, then divide by 2. Then do the same, sine square theta is equal to half, take the root, then you get plus or minus 1 over the root of 2. Then we just take sine minus 1 again, then we reach that we have 4 angles which has half power, and this is expected because we have 2 maxima. So around these 2 maxima we have half power from 2 sides. So where is this one? This is 45 degree by over 4. So in this direction it's approximately 45, and also here in this direction we know that at some point we have 45. If we draw this one, actually we'll find that first we know that 1 over root of 2 is approximately 0.7. So the length here at the half power is approximately 0.7. So similarly here, so this 4 point is just equal to 0.7. Then we plot our pattern. So let's bring another color here. So this will look like this, and it will keep decreasing until it reaches 0. And in the other side also it was here maximum, it reach 0, then go back to the maximum again. So this is how the pattern will appear in the two-dimensional plane y and z. And I actually plotted also it with Python, substituting by this sine square theta, but of course here this little bit reversed, because this one actually you should consider this one is z axis and this one is y axis. Now we move to the final step, the other plane, which we are requested to plot the pattern there, which is theta is equal to 90, and we discussed that this one is just the xy plane. And actually if we substituted by 90, originally our bar density normalized of course is equal to sine square theta. If we substitute here by theta is equal to 90, what you will get simply 1. So if it was 1, actually we don't need to do the calculation which we have done in the previous slide, because it's just a constant everywhere. There is no null and there is no maximum, it is just flat. So simply what we will have, if we plot the xy plane, we'll just get a circle, right? So this is maximum of course 1 because it's normalized, and this is xy. And I also plotted this one with Python, but this very easy, right? So if you look from any angle, you will just any phi angle, because here we are varying phi, right? In the previous slide we are varying theta. So at any angle, you just it's a circle, so it's equal everywhere. So what we have learned in this video, we have learned that the radiation, how to plot the radiation pattern, of course, and we have learned that this plot can clarify how the radiation occurred around the antenna in the far field. And we have learned also that this half power beamwidth and beamwidth between between nulls show how much focused is the antenna radiation in a specific direction. Stay tuned for more videos.